Good morning. I turn on. Good morning. As Professor Hugh said, today we'll be going to talk about flight of monarch butterflies. My name is Alper, my friend Raj, and Srinivas. So here's today's agenda. First of all, what makes unique of these monarch butterflies? Maybe their wing structures. We'll be closely examining this, and we will touching on what's the roller bearing effect. And later on, my friend Raj is going to talk about air drag on monarch butterflies, and he is going to be giving some mathematical background. Then my friend Srinivas is going to talk about the effect of the scale inclination on drag, extension to the shark skin, and lastly we'll be going to talk about the engineering applications of this monarch butterfly. Here is the video of monarch butterflies wing structure. Here's our friend. It likes flying, of course.
The
And
monarch butterfly.
they like migrating, which I'm going to talk about. But what makes them unique is their wing structure. If you check this wing structure closely, you'll
The
see
monarch butterfly.
numerous tiny scales. And here, okay, I'll pause.
The monarch butterfly.
I couldn't. Anyways, you have seen the scales. They have to do with the flight efficiency, which we'll be talking about. So what's our motivation? If you can see this map on the right, the monarch butterflies fly a lot. They fly very long distances. This is the US map. They prefer staying in different regions in different seasons. For example, in the summer, they prefer living at the west coast, and in summer and in spring, they prefer southeast regions. But this requires a lot of traveling, and flight efficiency should play a role in that. And do you think that they could travel that long distances because of only flapping, or are there any other mechanisms which makes them eligible to fly that long distances? And the answer is less flapping, more gliding. What means is this, if you can also see in this video, rather than flapping a lot, they like gliding. And they can do this because of the unique wing structure. Here is the scanning electron microscope image of this wing. As you have seen in the video in the slide 2, this is the closer look to the scales at the wing. This scales has micro cavities, and this induces no more no slip effect. What does it mean? It means simply the roller bearing effect. So what on earth this roller bearing effect? Here's the description of that. First of all, vortices form during a flight. This is inevitable. But with the help of this wing structure, these vortices are trapped inside of these cavities, as you can see in the figure right there. Rather than vortices forms over the wing structure, with the help of these scales, these vortices are trapped within these rectangles, let's say. And in different aspect ratios of these rectangles, vortices can be trapped in a different manners. You can see over here. And what happens, the overall result, the flow experiences reduced skin friction. The drag coefficient is not that much to reduce the flight efficiency. So in other words, these vortices act as rollers to the outer flow passing over them, because these vortices form rolls in that direction, which kind of accelerates the flowing at the upwards. So yeah, this is what roller bearing effect is.
So the conclusion that we have got till now is that due to this vortices formation, we do see roller bearing effect, which in turn basically reduces the drag. So on the wing, when butterfly flies, when the flow passes over the wings, it basically, instead of having no slip condition at the wings, we have instead of having no slip, we have roller bearing effect. So that essentially reduces drag. So before that, let us see what drag means and what kind of drag are we talking about. So we all know there are two types of drag. Usually if we take a classic example of flow past a circular cylinder, then we have form drag, which is due to the pressure gradient at the front and the back of the cylinder, and due to the skin drag, which is basically due to viscosity and boundary layer formation on around the circular cylinder. Now, in case of butterflies, the pressure drag is almost negligible, and the reason is due to the streamlined body or the streamlined structure of the butterfly itself, because the wings are too thin and there is no enough area. So first of all, the pressure gradient is very less for the butterfly, and the second, the area, cross-sectional area of the butterfly is less. So in that way, form drag is almost negligible for butterflies. But skin drag is considerable, because skin drag depends on the surface area, not cross-sectional area. And butterfly have considerable amount of wing area, which essentially results in surface skin drag. Now, if we take traditional butterflies where they do not have this scaling structures like this, then no slip boundary condition happens, and we all have studied flow past a flat plate, which induces drag on the wings. But due to the presence of these scales, the drag reduces, and we will see in the later slides how it is reduced mathematically. Yeah, we all know that when we ride bicycle or when we run, the predominant drag that we experience is not skin drag, it is pressure drag. Like when air hits us, it causes a pressure drop on our upstream and on our downstream, and due to which we experience form drag. Now, let us consider this mechanistic viewpoint, where we try to understand what's happening using our governing equations and boundary conditions. Now, let us first of all consider a case of without scales, where we have no scales present on. So this is wing, these are our wings. So this is without scales. By without scales, we mean wings are not having the scale structure. And with scales, we mean we have taken a very simplistic model where we assume the scale angle is 90 degrees, and it is like W1, W2 is the thickness or the width of scales. In usual scales, what happens is W1 is almost negligible. The scale thickness is very thin, and W2 is almost, so W is almost equal to W2. Now, let us consider case without scales. We have our control volume here. Now, by the definition of drag, drag is something which is force difference between this phase and this phase. Because on 1,4 phase, there is no gradient of velocity. Yeah. And so we have 2, 5, 8, 3. So these 2 to 5, 5 to 8, 8 to 3. These three are the forces that result in drag. Now we can clearly see here that all these add up and they all are positive. So the overall drag is positive. Whereas in case of with scales, as we have already discussed, we see this embedded cavity vortex inside this structure, due to which at the bottom of the scale, for example in 6-7 region, the velocity, the direction of velocity is from 7 to 6, which essentially results in a positive drag. So here instead of having a instead of having a drag, it essentially results in a thrust. So we can clearly see that the drag here is all positive, and here we have this negative, which makes the drag without scales much higher than, not much, but considerably higher than with scales. And with this simple analysis, when we try to estimate the coefficient of drag, we see it is of the order of 2 over Reynolds number. This is without scales. And with scales, we see it is of the order of 1 plus d by delta, where delta is our boundary layer thickness. So here d is the length of the scales, and delta is boundary layer, this distance, boundary layer distance. Now, a fair estimate would be to assume that the percentage, the d by delta is almost 10%. So this length d is 10% of the entire boundary layer. Then we can clearly see for 10% scales, when d by delta is around 10%, our drag coefficient is reduced by 9%. So with this simplistic model, we are able to come to a conclusion why this happens. And like this is a simplistic model. To do a full scale analysis, we definitely need to solve full Navier-Stokes equation along with boundary condition. And people have done few experiments through which they found that for the scales, in the presence of scales, we see the coefficient of drag is 1.33. Whereas in the traditional flow over a flat plate, it is 1.48. So we can clearly see a decrease in the drag. Yeah.
Okay. So this is the flow visualizations over these structures. So they basically considered three inclinations, that is 90 degrees, 45 and 22 degrees. So the phenomenon we are basically talking about is only valid for very low Reynolds numbers. So that's precise, like till until 10, and beyond that you will not see the roller bearing effect. So essentially, as Raj and Alper explained about it, so the roller bearing effect, you could see it here, right? I'm just pointing it with my pointer. You could see there is a concave kind of streamline. So basically, when the flow is flowing over that, so you don't really essentially have that no slip condition. So it just glides over it. So it's almost like a partial slip. So that's why you have very less drag. Whereas when you come to higher Reynolds numbers, so this is 170. So this is ideally not seen in nature for a butterfly. But if you look at the way the vortices are formed, they're kind of more turbulent, and basically they tend to even interfere with the basic outer flow or the general flow that's going on. So what happens is like that's when you see a drag again. So increase in drag. So and the aspect ratio is 2 for all the images. So again, these are the CAD drawings of the ridges or the structures, and again these are like 300 times magnified. I mean the structures are very small, at the order of microns for butterflies, but then for this analysis, so the authors of this paper basically they fabricated it like at the size of 300 times of it, and they used oil and particle image velocimetry to basically get those streamlines in the previous slide. So these are the results. As you can see, generally with the decrease in inclination, you are able to see that the coefficient of drag is also decreasing. So this also could be extended to shark skins. So we know that sharks tend to swim very fast. So the reason is again because of this micro vortices that form between the microstructures. Essentially, for a shark, the only difference is it is dynamic. The structures are dynamic, right? When the flow is flowing over it, initially the structures tend to be flat. And then as you see some kind of a pressure gradient that's developing, so the vortices form in between the structures over here in general, and then slowly they tend to flare up. And then once that kind of a pressure gradient is like suppressed, it'll again get back to being flat. So that's how it is. And then some real world examples and applications would be, so there's a swimsuit that has been inspired by the structures of a shark. So what happens is it's basically a hydrophobic kind of a material, so that there is less drag and basically, I mean, yeah, there's less drag while you're swimming, right? And then again, bio-inspired aircraft design. So we know that the winglets, a very common application, but not very close to this, but yeah. So essentially to reduce the vortices that's formed while the aircraft is taking flight. Yeah, that's all. These are our references, and thank you. Any questions?
Maybe one or two questions, audience.
Yeah, please.
So do the butterflies try to stay in the Reynolds number regime of like 1 to 10?
Yeah.
Okay. Did you guys come across like what they usually, the Reynolds number for them like is? Well,
It is around 10.
It's 10? Okay, that's cool.
For
So that scale that you use for the Reynolds number?
On like the wing scale, the scales on the wings of the butterfly.
Oh, the base of the
Yes.
cavity
Is the
size.
cavity size.
That Reynolds number is 10.
Yes.
Yeah.
any other questions?
Go back to your model. That was actually pretty.
Which one?
Uh,
This one?
Yeah, this is pretty interesting. So you have basically like have control volume just of your solid surface.
Yes, just to a solid surface, so that when we do mass balance, we need not really bother about the influx and outflux of the mass.
And the sides of your cavity, those balance out somehow because those are just like
Yes.
down. This is from the paper. Or this is from
This we have done very simple analysis on our own.
Oh,
In the paper, they have presented this final result.
okay. I see. Oh, why is I don't understand why. So without scales, that's the Reynolds number.
Yes.
That's experimental relation, right? Basically, that the low Reynolds number goes.
Yes.
High Reynolds number goes.
This is our analysis, and in a paper where they basically assume W1 to be negligible and D to be almost order of delta. This is like a typical drag coefficient that they have found. So it is 2 for without scale, and this is for inclination angle of 90 degrees. But when people have done experiments and on real butterflies, they have found that it is not 2, it is 1.33.
Okay. Where does D over delta come from? For
D
this?
over delta, yes. D is this thickness of the scale,
Yeah.
and delta is the overall boundary layer thickness.
Yeah, right.
So in our drag, we will have the stress component, and stress component is a function of delta.
Right.
Stress component is a function of boundary layer thickness. Now the stress varies from 2 to 5 and 8 to 3, and it also varies from 5 to 6, 6 to 7, and 7 to 8. So when we have this recirculations inside it, the velocity profile inside this cavity is function of this d distance, because this geometry using the boundary conditions inside 5, 6, 7, 8, we have to take into account the distance d. So the velocity in the velocity profile we have d, and from that velocity profile when we take the gradient to calculate stress, I believe then we get that d by delta.
Okay, so the velocity in the cavity goes as like the boundary layer
Yes.
height, and then you also have the shear stress.
Exactly.
The gradient.
So here we need to do the stress mapping at phi 8, like solving in this domain once and then solving inside the cavity.
All those pictures, those are with some mimics. Those are not actually with butterfly scales, right?
They are they are done on
2D surfaces.
They manufactured those surfaces by checking the butterfly wing structure. Yeah.
And go to the last one, the shark scales. So, so basically there are a bunch of swimsuits, like one of the first Olympics to use those shark skin swimsuits, people broke records. But in those papers, they basically said the reason they're breaking records probably does not have to do with the drag reducing capabilities. It's probably more to do with the fact that you're just squeezing people's cross-sectional area. Just squeeze your fat, like you make it more streamlined. Because they did careful experiments they took shark scales and put them on plates, and basically the drag actually somehow went up. And so they found that sharks can do it because it's the interplay between the flexibility of the scales, like the effects you've shown here, and the fluids. So if they have flat, rigid plates, the drag goes up. If they have flexible plates that flap long enough, then the drag can go down. So they still haven't been able to make suits that drag reduce in the same way. I mean, because we don't swim the same way as sharks. We're basically like, very rigid, and the sharks are doing like this kind of thing. So that Physics Today paper talked about shark scales too?
Exactly, it references.
Any other questions? Okay, good.
Great, thank you.
Groups of 3, I think you guys will be destined to take longer time, but I think what you're talking about is interesting. It's okay to go into Q&A.
Yeah.
Okay. So the homework. All right. A little bit about strain and vorticity. We're going to have 2 demos this week. This is one built by my undergraduate class. They wanted to figure out a way to roast marshmallows faster. So, let's see what all right. So in the homework, so basically there are a couple of things you can measure from a fluid. One of them is this quantity vorticity, which is basically just the curl velocity field. And it has units of 1 over time. Now this little demo is an example of what's called vortex stretching.
I don't know if your mic is on. Can you just check to see if it's out?
Oh, I probably didn't turn it on, sorry. Thanks, Jeremy. All right, so let's see. This is, we just got a motor here, got a little candle. This is Ethan's hairband, which worked really, really well. I haven't done this demo in class before. I feel like I'm going to burn the doc cam. So maybe, let's just, wait, I'm not going to be smart about this. All right, that seems like a little safer. All right. Okay, so first of all, what is this thing? This is, what this is going to do, I'm going to do 2 things. I'm going to pour some alcohol into this cotton ball. So basically, it's going to, when we light it, the flame is going to basically burn this, and everyone knows a fire rises because as it gets hotter, it gets less dense, and it goes upward. Now, I think what you didn't know that if I basically spin it, the fire is going to get higher, and the reason for that has to do with we're going to derive this basically this vorticity equation that tells us vorticity, which is basically the curl of the velocity, and it's going to tell us how much spin you have. And when you have basically extra strain, so what we're going to do is add more vorticity, and the flame and the lower density is going to have a velocity field that goes upward. Basically, we're going to show that you can increase vorticity, increase your curl. The fire is going to get smaller and faster and taller when I basically have the combination of the buoyancy, which pulls the fluid up, and the spin. All right, so I'm going to splash this. No. Let's be professional here. All right, so I don't have anything. Oh, I spilled some already. Oh, spilled some.
Roll because it died.
I just all right. All right. That seems fine. All right, so that's how high the flame is, and when I turn the spin on, I think it only has 1 speed. Oops, that's too fast. Sorry. I think this little valve can make it slower. All right. Did I just break it? Oh, you see how I got it taller?
Oh, yeah.
But if I do too fast, it's going to basically make the flame go out. So it does get taller. So that's low speed, and then I basically pull more, I increase the spin, and that allows this vortex to stretch. The vortex is basically visualized by the flame. That's how tall it is. So I'm increasing the speed. Oh yeah, that's really high now. I lower the spin and it goes back down to normal. Yeah, there we go. The amazing thing is you don't actually even need spin. I think this is constructed carefully. Just the presence of these things will make the flame higher, because as it draws in air, it has to draw them past these things, and because it has to go past this thing, it causes a little bit of spin, and this will stretch. But I don't think I can do it. I don't think I can do it this carefully. Take this out. If I had another candle next to it, this candle should be a little bit higher because of just the presence of these veins. Oil fire, do you blow it or you cover it? Okay. All right, good. All right, so we're going to talk about what you saw there. We have to, basically that vorticity equation is an offshoot of Navier-Stokes equation. Okay. And I sent a link about the office hours for today and tomorrow. I think Layla's coming at 2 or something. Did you? Oh, 1. You came at 1. I also teach a class of about 70 undergraduates. So if there's like a lot of undergrads in, I'll try to take care of you first, because otherwise they're just going to take over. But maybe if you come at the beginning, I can try to take care of people. Otherwise, we'll have to go in between because it's a different subject.
And I'm sorry,
Yeah.
Still doing office hours at 8?
Yeah. Do people like that? Yeah. I think because the online people, they can only do 8.
Right.
Yeah. So we're going to do the evening one. And the homework is due. So homework is due Friday. Homework 2. And I'm going to pass out homework 3 soon. All right. All right, so let's consider 2 points in the fluid. So a point P and a point Q. All right. So there's going to be this displacement vector r that goes between points P and Q. That means if this is the origin, so this will be, we'll call this x. I got to erase this. And this will be, if the position of P is x, then position at Q is going to be some x plus some amount r. And we're going to look at basically what can we say about the change in velocity between here u of x and here I'm going to make it vastly different, u of x plus r. Okay. So we touched upon this briefly last time. Not last time, but it's kind of like before we got distracted by quiz 1, that the velocity at some point away from x can be written as the velocity at x, okay, plus basically how much distance you have in between them. So all of you know the 1D Taylor expansion. When you have 3 dimensions, it just means you have this terms instead of the first derivative, right? All right. So basically, that's how that you can write the change in velocity. Is the initial velocity at the initial point
plus basically how much u is changing in all three directions, x, y, and z, which is given by del, and you have this r, which is a three-dimensional version of what you probably already know.
And what's that third term just saying that everything beyond that is 0?
Yeah, this you say this is order r cubed. And the whole idea with these Taylor things is that you want to have r to be really, really small. So they get basically less relevant as you get to higher order. Okay. So basically, how much u is changing? Now imagine that all these points, x is a function of time and x plus r is a function of time. So all these points are moving around. But the relative, how much the velocity is changing is going to be given by this. So this is, we call this the relative velocity between P and Q. And this is going to be an important part of how we calculate strain. For the homework, you kind of had some steady state velocity fields where basically you calculate, this picture of what the velocity field looks like. But for the next homework, we're going to be doing time-dependent stuff. So basically, all the points of the fluid are going to be moving around, but you still can calculate strain, okay? But you have to use this material derivative because stuff's moving around. So this change in u, we'll just write that as the difference in u between those 2 points. So u at x of plus r minus u of x. Okay. And we just get rid of those higher order terms. So we'll have r dotted with del u. And then from the homework, you've also practiced writing the information in the gradient of u. Remember, that's a tensor. It's 3 by 3 because each direction you have derivatives for each of the 3 independent components. Okay. Plus higher order terms. Okay. And remember, this is the velocity gradient tensor. Where, just to remind you, we'll be doing this a few times a day. We're going to split u into the 2 parts. What we call E plus omega, where E is symmetric, and omega is antisymmetric because we subtracted out the symmetric part. So this should be, this last part, just a review, antisymmetric. So the change in u, we can basically written as r dot e plus r dot omega. Oops. We're just substituting those 2 parts for gradient of velocity. So let's do a few problems to figure out what's the phasal significance of E and omega. So they actually contain information about the flow. As we'll show you, and I think some of you have already done the homework. Remember, omega is antisymmetric, and also from the quiz, antisymmetric matrices, so remember, so E basically is symmetric. So basically you've got 3 components here, and you basically you've got 3 components here. So you've got 6 components. 6 components. I don't know 6 components, but 6 pieces of information. 6. I'll just call it components. Right, you got the diagonal and you got the off diagonals. But omega, remember from the quiz, we learned that omega has to have 0, 0, 0 on the diagonal. That's the only way it can be antisymmetric. Because remember, we have Eij is equal to Eji, right? But omega has this property that omega ij is equal to negative omega ji. And that means the diagonals are 0, and that means you only have 3 components, 1, 2, 3. And as you've done from the homework, you've shown that, well, physically, the stuff in this omega matrix, that corresponds exactly to vorticity, because vorticity has 3 components. You know, in this problem, it's all in the vertical direction, but if I tilted this thing, it could be like in any of those 3 components. So little omega, the vorticity that we talked about in the very beginning, information is in the capital omega. Okay. But how much the vorticity changes is a function of E, how much strain you have. They get interplayed once we derive the vorticity equation. Questions? Is that okay? Okay. All right. So let's talk about the rate of strain tensor E. So that's how people, that's very verbose. So I'm probably just going to say E. But I think if you're really precise, you tell people, oh, that's the rate of strain tensor. So this is the symmetric part of U, symmetric part of the velocity gradient, right? And we've said that, hey, with Navier-Stokes, basically if you have P, the pressure, sorry, this is not grammatical, with, along with the pressure, prescribes the state of stress in the fluid. We argued last time that basically omega, the antisymmetric part, just talks about rotation, but you don't have any relative motion between particles. E has all the information about relative motion. So we're going to take equation star. I'm going to label an equation back here. So basically, this equation, we'll call that star, the dr dt equation. This is the dr dt. Inner product of star with r. So we're going to dot it with r. So if you have dr dt dotted with r, remember the r dot e. So that was what we had before. I'm going to dot it with r, so we have this. So I made a simplification. This e is supposed to be del u, but we're using this identity. We're using identity that you proved. This is a homework 1, number 4.x, so 4.10, that r dot omega dot r is 0 because omega is antisymmetric. So this is supposed to be a gradient u, but because the antisymmetric part gets killed when you dot it with r again to the right, you only have this. So if we do a simplification, the next step is r dot r. And I think we've done something like this bar before. You basically get this. All right. So now we kind of have something that means physical sense. So remember, r was the distance between those 2 random points in the fluid. So this is the length squared of the displacement vector. It tells you basically, how close your fluid particles are. Okay. The bigger this is, the farther apart they're going to get. And this says that, hey, our fluid, those points P and Q are going to get larger and larger distance if this r dot E dot r is positive. So this prescribes the rate of change. Of r. So you basically have strain. If your rate of strain tensor has some non-zero values, it means points are going to get farther and farther away. If this thing, remember, E is a tensor. If I dot it with two r's, those are going to be a scalar. This left-hand side is also a scalar. So this tells you if it's positive, it tells me my points are going to get farther and farther away. If it's negative, it means that I've got negative strain, and it's going to get closer and closer together. Okay, so E tells us how far points are going to get away. That means vorticity is not going to tell us about distance between points. It's going to tell us about spin. Okay, so that's all we're going to say about the strain tensor for now. It's going to come back when we derive the vorticity equation. All right, let's talk about the vorticity tensor omega. Remember, that's the antisymmetric part of velocity gradient. So in your current homework, you're going to show that basically omega, and I kind of drew it pictorially, has all the information of vorticity, where basically you have the permutation tensor dotted with the vorticity. So basically those three elements in that the upper right of the matrix has the components of omega, little omega. So remember, this is vorticity. And this is, I don't think this one has a word. This is just the antisymmetric part of U. Part of del U. Where big sigma does not have any information. It just basically is a bunch of plus ones and minus ones according to the following notation, where we have the permutation symbol EI, EJ, EK. Just like epsilon EI GK has 27 different values, then this big sigma will be populated with those things. Okay. This is the permutation symbol as before. Okay, if someone asks you, like on the street, hey, what is vorticity? You can just say it's a measure of the local angular velocity. This is evident when we try to examine the contribution of omega to the delta U. All right, so let's do basically r dot big omega. We're going to use our substitution. And we're going to go to index notation. All right, this is a good time for you to practice and simplify this for me. Let's break for like two minutes, so you can you want to basically pull this into index notation, and then we want to pull it back to vector notation. But I want to get something that's has omega, little omega, and r. So substitute using that definition of big sigma. And then rewrite it back in vector notation at the end. Yeah, so this, yeah. Oh, okay. Yeah. So we got Ri. That's fine. And okay. Now what's the next step?
So yeah, I was wondering if it would make more sense to start inside or
It doesn't matter.
it doesn't matter.
Yeah. But so what are you going to dot this one with? What's that? You're going to hit. Is going to hit the closest one, EL.
Okay.
And this one to hit that one. Okay. That's correct. All right, we've got some winners. All right, let's go through this. Okay, so each index has a new notation: RI, for the radius vector. Keep the dot product, which is going to copy this. But of course, we already use I, so we can't use that anymore. So we'll call this LMN. That's what I saw some people do. EL, EM, EN. And we have another index for the omega. Omega, we'll call that K, because we kind of like ran out of stuff. All right, so this information, you got to use the what's closest. So basically, N is going to hit the K, I is going to hit this one. So you have 1/2. You can have RI. Let's just move all the stuff. Omega K to the front. Epsilon. So this epsilon, L is going to be an I. M is going to stay because it didn't get touched. N is going to be hit with a K, IMK, and we're going to keep the EM. All right? All right. So clearly, the only thing that left now, we got R, some component of R vector, some component of omega, and this epsilon. This epsilon screaming that is basically a cross product. So let's rearrange it to a version. I'm going to just be super, super pedantic. Rearrange a version, something that we know. Negative epsilon IKM by doing the property of epsilon, switching the M and the K. IKM, RI, omega K, EM. All right, now this looks exactly something like we know, because this is going to be negative 1/2 R cross omega. And I will also accept nega of 1/2 omega cross R, because the cross product, you can change the sign. Good. All right, so physically, what do we start with? We said, hey, what is R dot omega? Well, that is basically just this vorticity vector cross R. So physically, what it looks like is if you've got basically some point here, your omega vector is coming out, your R vector is going out here, and how much information is R dot omega is simply given by omega cross R. Okay. Yeah?
So your physical example was that an interpretation of the omega vector based on?
Yeah, omega is going to be the vorticity. So if, like, back to this fire whirl thing, let's say it's all planar. The velocity is all in this direction. Omega is going to be just vertical.
Okay.
Yeah.
If you switch the direction, then it would go down. Decrease the height of the...
Oh, you mean how do I, these two negative signs you're saying? Oh, you mean where does that 1/2 come from?
Yeah, kind of.
Yeah, it basically says, we played this game, this R dot omega. So where did we do that? We did an R dot E. We looked at R dot E before. Let's go back a little bit. All right, so this is how much strain, this is how much the change in velocity is between 2 points. It tells you how much the points are separating. And now we see that, hey, if I basically look at how much the points are separating, they're not separating, they're just spinning. So physically, let's say we're going to call this a point P. This represents a rigid body rotation. About P with angular velocity, which is basically given by the magnitude of omega over 2. So the reason why this is different from the rate of strain matrix is that the amount of change in the velocity points is perpendicular. It's coming out of the plane. The other one was kind of like in the plane. Okay. So here it's all the points are just spinning, and the spin rate is magnitude of omega divided by 2. So physically, oh, that's terrible. Omega does not change the length of r. Or impact the state of stress in the fluid. All right. So this vorticity, another way you can talk about vorticity is the circulation. So we said vorticity is the local angular velocity. Vorticity is also related to the local circulation. If anyone's aeroastro here, circulation is really important to figuring out lift forces. But circulation is basically, here, let's draw a picture first. If I've got basically some surface, we got some surface area C. Some surface area S that's bounded by this closed contour C. Circulation is defined as if you basically have a net velocity gain as you go around the point. So as you know from the divergence theorem, this definition of circulation can be written as n dot this, n dot the curl of the velocity, and that can be written as n dot omega ds. Okay. This is by Stokes' theorem. So how much circulation you have is basically, you can imagine as s goes to 0, so we can write n dot omega equals the limit. As basically we shrink it down to a point of the circulation. So if you basically have a non-zero vorticity, you're going to have some circulation as you go down to a point. And you can imagine, what is circulation? It's basically you're integrating your velocity as you're going around this closed contour. So if that's non-zero, you can imagine that means your thing is kind of spinning around, right? So that's also related to, when we say the angular velocity, it's kind of like defined at a point, but basically as we shrink s, you're kind of getting closer and closer to that value. So whether you have things sort of spin around or not has to do with the vorticity, and that has to do with circulation. Let's consider rigid rotation in cylindrical coordinates. All right. So in cylindrical coordinates, so to remind you, basically, all right. So you got x, y, z. Cylindrical coordinates defined by two values. basically your radius and your height here. So something like this. So rigid rotation in cylindrical coordinates means that basically your velocity field is simply given by your position, okay? Where your position here is simply, you got r hat plus z hat. Okay, so the closer you are to the origin here, you're going to have less velocity, and the farther you go out, the higher velocity you have. That's what this says. Okay. So let's calculate what the vorticity is. And I'll drill another. So all right, in this case, your F is going to be Fz hat. Basically, it's going to be it's spinning this way. So let's say we have some spin this way. You have your Fz hat. That's direction we're spinning around. So U is going to be Fz hat cross, and we're only going to take the component that we need, cross r hat. And that's going to give us Fr theta hat. All right, so to remind you, we take like the disk. R hat is kind of going out, theta hat is going in the azimuthal direction, and z hat's going up. Okay. So the velocity, and this makes sense. This is what we were saying physically. Hey, at r equals 0, the velocity is 0. But the further you go out, you basically have increased velocity associated with your radius. Z cross r is theta. Now, how do you calculate the vorticity? Remember, vorticity is the curl of u. Now, you got to be a little careful here because this is cylindrical coordinates, and in cylindrical coordinates, nabla is really is weird because everything depends on theta. So I'll just tell you what this is. You can practice on your own. In cylindrical, let's say we have a vector A is r hat plus a theta hat plus a z hat. Then the curl of A. It's going to have a lot of components, but the stuff that's relevant to you is going to be this for this problem. D by dr of r a sub theta. Okay. And in this case, if you substitute it in, you're going to get 1 over r d by dr of r squared, fr squared. If you pull that out, you get f 2. In this case, del cross u is 2f z hat. Okay. I don't think we actually do very many problems with cylindrical coordinates, but if you do encounter one, you have to make sure that you don't treat it like Cartesian. Okay. So in other words, omega is 2 times f, which is kind of what we had before. We had basically that the spin, you got some spin, and your vorticity is basically twice the spin. What we had before was 1/2 omega cross r is r dot big omega.
F is what? That's this, you said it's the spin?
Yeah, f is given is basically, so this is given is basically how much the rigid body rotations. Basically, it tells you the direction that it's spinning around the z-axis, and it tells you the frequency. like the rotate. This is like rotations per second per time here. Okay, and the question is like if basically if this entire thing is rigid body rotating. So it's like if I had a record player that was spinning a fluid, and the steady state position of the fluid over time would look like this. And we're saying, hey, if in this situation of a record player spinning a steady state fluid, the vorticity is just twice the spin. Okay, and we call that rigid rotation because it's like the entire fluid might as well be a block of ice. It's not getting any relative motion between points. The whole thing is moving as one. Okay. All right, so that's enough intuition about vorticity. Now, how does vorticity evolve? And this actually has a lot of influence on turbulence. This won't be a class on turbulence, and we're not going to really talk about it beyond today, really. Turbulence, there's a lot of statistics that we're not going to deal with. But basically, if you notice in a turbulent fluid, what goes on is that you've got big eddies become smaller eddies. And smaller eddies become even smaller. I think there's some fluid mechanists that wrote some poem about it. It's like smaller eddies go smaller. But basically, they get smaller, but they get longer. And that's this idea of vortex stretching. Those eddies you see, those velocity, those vorticity vectors are pointed in all random directions, but you imagine they're all getting smaller and basically longer. And that has to do with the vorticity equation, which we're gonna derive now. So this tells us the evolution of vorticity, which is the local amount of spin in a fluid of vorticity. Evolution meaning like how much vorticity you get after you come back an hour later. And physically what's going on, you got big eddies going to smaller eddies, and as they get smaller and smaller, eventually it's all going to become heat. But it's got to get like kind of dispersed throughout the fluid first. All right, let me tell you what the vorticity equation is, and then we're going to derive it. So this is the vorticity equation. We got d omega dt is equal to omega dot del u plus nu del squared omega. Okay. This is the vorticity equation. So this tells you how much vorticity is changing, the advection of vorticity. Okay. This is what we call vortex stretching. It's basically demonstrated by the demo we had. So in our case, the vorticity of that little flame was increasing. The angular velocity of that flame was increasing. And the reason was because we had a velocity gradient. In that case, we had some component of the velocity gradient with the spin. So this thing is, the velocity, the omega is all pointed upward. But because the thing is hot, it's rising, and so that combines it to increase my vorticity. That's why it looked like it was spinning so much faster, and that's why it got stretched. It got longer. Okay. This is the diffusion of vorticity. So vorticity is like a quantity. You can have some parts of the fluid that have spin and others parts that don't. But over time, if you wait long enough, that spin will get dissipated everywhere. But the problem is we've got a lot of space everywhere, so it eventually just kind of damps out. And this equation says we got diffusion of vorticity down vorticity gradients. So in other words, places that have no vorticity get more vorticity. All right, so that is the equation. So maybe you've seen something like this. This is similar to the heat equation. But not with energy. And we also have this stretching term. Let me give you a little bit more the class ends in 10 minutes, right? I kind of want to leave you last time with some intuition about this equation. And we have the derivation, but I feel like the derivation is less important. So we'll get to the derivation last time, or maybe I'll just make it a homework. Okay, let's talk about vortex. So let's talk about vortex stretching. All right. So, and let's just consider inviscid flow, where basically the vorticity is not going anywhere. So it's super, super high Reynolds number, and the viscosity is like negligible. That's what inviscid means. So let's dot this vorticity equation, dot inner with omega again. With omega. So then we have, just like last time, we have d by t of omega dot omega is equal to omega dot, let's separate u into these two parts. And we already know that omega, basically anything dotted with the antisymmetric part dotted with itself is going to be 0. So this just becomes this. Omega dot e dot omega. So we see the rate of strain is not just important for changing position of vectors, the position of your fluid, but it's also important in changing vorticity. This means that vorticity is amplified by local strain. All right, so in the example we had, basically, we kind of had like a large, so this is the direction that stuff is spinning. We had a large, slow vortex. And that became, as I increased as I spun that around, it became a smaller, faster vortex, all around the same axis. So it'd be a small, faster vortex. And that's the tendency where stuff tends to go if you have a strain. And this is similar to what they call the turbulence cascade. Cascade is like, physically, it's like you going down a waterfall in Hawaii. But here it means like going from vortices of large size to smaller sizes. In other words, big eddies become small eddies. Fast eddies. And as it gets smaller, eventually they become heat. Okay. So two things from this example. So basically, you got vortices that stretch. Will tend to stretch over time. There's one counterexample where they don't do this, so imagine, basically, you got this length, this length, like you saw the length of that fire whirl. It was only like, an inch high before. So this is the demo. It was like 1 inch high, and this became like 3 inches high, 3 inches high. That's suppressed if you have something called a vortex ring. Can you imagine, because vortices like these vortices like to stretch, but basically if you're already in a ring, it's like this whole thing is connected. So this would want to stretch, but imagine if basically the whole thing's connected in a circle. Like a vortex ring, is basically this whole thing is connected in a circle. So it wants to stretch, but it can't. So this is an example why they're stable. So vortex ring is stable because it resists stretching. What goes on if you blow a smoke ring or you see those dolphins blow ring? Those rings dissipate by viscosity. So, for example, we had this other term. They basically kind of like the ring slows down and it kind of gets fatter and wider. The reason it slows down is because if it gets fatter by conservation of angular momentum, it's got to slow down. And if it's get fat enough, it just kind of like you don't see it anymore. But it slows down. It slows down to satisfy conservation of angular momentum. Another example I want to leave you with is with piers. All right. So so I'll call it bridges for now. All right, so imagine if you okay, let's do a little, my art is not going to be so good. So basically, you have this, my bridge kind of looks like a table, but you have water flow. Let's say this is the seabed, okay? And this is a sediment. Sediment. What goes on is that if you've got some water flow, let's draw like a view like this. If I got flow, let's say I got uniform flow going on the sediment, and so just we saw from the butterfly, this nice butterfly talk, you're going to have basically a velocity gradient, so you get no slip on the bottom. But let's say we have these what we call piles. So this is what's called a pile. Those like big log things that hold up bridges. Now the problem is that as the fluid hits this pile, there's a downwash, and that downwash basically has some velocity here, and furthermore, fluid's got to go around this thing. So because of this downwash, so you can imagine this is my velocity field here. My omega is going to go into the page. Omega is going sideways, and I'm going to get basically these vortices here that are going to cause. This is called a horseshoe vortex in the front. Horseshoe vortex. And it's going to cause what's called scouring. Scouring is generally bad for bridges. From what I read, there's 1,000 bridges in the US that have failed, and 60% is by scouring. It's because over time, if you've got a river, I wish I could draw this better, but like you had, basically, you have like this dip of, basically you lose the sand in this kind of like horseshoe pattern around because of the velocity field and the velocity causing the vortex to stretch and to get more powerful. So that's an example of the vorticity stretched and it gets stronger and it basically helps the scouring effect. This fire tornado thing also happens in like forest fires and things like that. If you basically spin something spin a fire which already has a velocity gradient, you'll get a much stronger flame. Okay, I didn't derive a vorticity equation for you. I think we can do it a little bit next time. It's basically 3 steps, but I think we probably do some kind of in-class activity that I give you the 3 steps and you do it. It's one of those things you want to do once in your life, but probably not more than that. But if you don't do it once, you won't understand where it comes from. But it comes from Navier-Stokes, and we do some simplifications. Okay, so I'm going back to my office now. I'll be around until, I think, 3 something. Some undergrads are going to come around, and I'll be in my office again at 11 tomorrow. Homework is going to do Friday. Oh, so next time we're going to do a demo, except we're going to do a demo at your seats. So if you could bring a water bottle, bring your water bottle to class. I basically have 30 Shumanagashi platforms for everyone to do it, but I don't have like 30 water bottles because I'm biking. So if you could bring, like, we don't need that much, but like, you know, like 16 fluid ounces. We're going to do the Shumanagashi tomorrow on Wednesday in the beginning of class. And that'll give you some insight into do the soap boat problem where the boat is being pushed by the oily rag.
Professor, what kind of water bottle? You like a plastic water bottle with water in it, or like an empty bottle?
I just need the water.
You just need the water.
But we need water to basically fill the plastic tray so we can add ink on top. It doesn't have to be that clean. It can be water from outside.